Welcome back to The Explainer. Today, we are exploring an absolutely fascinating hidden history. We're going to uncover the invisible thread connecting your fingertips, early sensory engineering, and the highly abstract mathematics that literally power the modern internet. We often think of digital computing as this disembodied, abstract realm of pure math and silicon, but what if I told you that the very foundations of information theory were actually forced into existence by the strict physical limits of the human body? Pretty wild, right? Okay, let's dive into this. We'll start with the sensory bandwidth gap, move on to the cybernetic feedback loop, look at mapping tactile coordinate space, and finally uncover the birth of information theory.
So, Part 1, the sensory bandwidth gap.
To truly understand the architecture of modern communication, we actually have to start with biology. We have to view the physical reality of the human body as a literal, massive engineering hurdle. Now, I want to anchor you with this massive number right off the bat. 10 million bits per second. According to the research, this is the estimated physical transmission bandwidth of the human retina communicating raw visual data directly to your brain. When you're looking at a screen or reading a printed page, you're relying on a massive, high-speed biological data pipeline. And this brilliantly illustrates our staggering biological bottleneck. Look at this comparison. While vision processes millions of bits per second, tactile reading, processing information strictly through touch, mechanically limits the fingertip to under 100 bits per second, less than 100. Your cognitive systems involved in semantic comprehension can process plenty of meaning, sure, but physically, the finger just isn't built to ingest data the way the eye does. It is a severe bandwidth crisis. Because of this severe physical limit, standard visual reading is fundamentally different. It relies on taking in whole words and shapes at a glance. It's a flowing, continuous analog process. Tactile reading, on the other hand, demands a rigid, discrete, slow-moving reality. Think of Louis Braille's six-stop matrix developed back in the early 19th century. You've got this 2x3 binary cell matrix, and you can't just glance at it. Your finger has to actively move and piece that binary data together sequentially. So how exactly does the human brain cope with restricted bandwidth and noisy environments? Well, it actively uses a mathematical concept called quantization. Basically, quantization is mapping a continuous, infinite set of input values to a finite, countable set of output symbols to prevent noise from accumulating. Our biological cognitive systems use this as a literal error correction mechanism. Think about Helen Keller at the water pump. She experienced a continuous, chaotic analog rush of water over her hand, literally infinite variables of temperature and pressure. But her cognitive architecture quantized that infinite variance into 5 discrete tactile symbols spelled into her palm, W-A-T-E-R. Discretizing that chaotic analog sensory stream into stable symbolic categories is exactly what allows us to process meaning without signal corruption. All right, moving on to part 2, the cybernetic feedback loop. We've looked at the biological problem. Now, let's look at the brilliant physical workarounds developed by early engineers to bridge this massive modality gap. If we trace the chronological evolution of sensory engineering here, a really clear lineage emerges. In 1824, Louis Braille creates his binary tactile code. Fast forward to the early 1900s, Alexander Graham Bell is deeply involved in deaf oral education and the mechanics of the material voice. And by the mid-1900s, Norbert Wiener is developing his hearing glove. We are seeing a direct evolutionary line from tactile writing systems straight to the birth of early telecommunications and mid-century cybernetics. Now, what's really interesting about this slide is how Norbert Wiener viewed the human body. He didn't just see a person, he saw literal hardware. His hearing glove was a wearable feedback loop designed to convert acoustic speech signals into distinct frequency bands. These bands were then delivered as vibrotactile impulses directly to a deaf user's skin. Wiener was integrating the material body into a physical communication circuit to restore interaction with the environment. It was an absolutely incredible hack of human biology. Which brings us to part 3, mapping tactile coordinate space. So how exactly do you take abstract symbols and forcefully map them onto human biology when you only have a fraction of the bandwidth to work with? Well, engineers realized they needed completely new tactile coding schemes. Enter Frank Geldard's FiberDes in the mid-20th century. This was designed as a high-speed, non-visual communication system, initially for high-stakes environments like military cockpits and industrial settings. Geldard and his team decided to literally turn the human body itself into a multi-dimensional coordinate space. Let's walk through the math on this slide because it is brilliant. Geldard broke tactile sensation down into 3 specific parameters. First, vibration duration, giving it 3 distinct steps. Second, vibration intensity with 3 levels.
And third, spatial location on the body, utilizing 5 distinct channels. When you multiply those together, 3 times 3 times 5, you engineer a state space of exactly 45 unique tactile symbols. They systematically mapped an entire alphabet directly onto the skin.
But of course, they were still fighting biology. Despite this brilliant workaround, humans still faced strict physical hardware limits. The skin's optimal frequency sensitivity range is only between 25 and 400 Hz. And because of the elevated cognitive load, the maximum reading rate topped out at around 38 words per minute. Plus, users were subject to rapid sensory adaptation. That essentially means the nerves in your skin literally get tired of vibrating and just stop sending clear signals to the brain. Our biological hardware simply couldn't keep up with the data.
Okay, let's move to part 4 and see how this all builds to the birth of information theory.
This is the ultimate twist of our historical detective story. But first, we need to define cybernetics. It is the science of communications and automatic control systems in both machines and living things. The foundational principles of modern computing didn't just emerge in a vacuum. They were completely and totally intertwined with the necessity of overcoming human physical limitations.
This quote from the source material is absolutely crucial. Listen to this. Modern information theory and cybernetics were not born out of a desire for disembodied abstraction, but were directly grounded in the physical realities of sensory disabilities. Think about that. Alexander Graham Bell's foundational work as a tutor for deaf children directly inspired the optimization of voice transmission over copper wires. Sensory gaps literally forced the invention of these solutions.
So let's summarize this historical arc. Step 1. Pioneers had to face severe biological sensory limits like blindness or deafness. Step 2. To solve this, they engineered physical feedback loops, treating the body as a coordinate space and quantizing data to fit narrow bandwidths. Step 3. The math and mechanics required to solve those earthly, tangible constraints laid the precise, rigid groundwork for modern digital communication. It is all deeply connected. The Shannon-Hartley theorem, which defines the maximum rate at which information can be transmitted over a communications channel, and Claude Shannon and Harry Nyquist's concepts of channel capacity, were built directly on the observations of bandwidth limitations originally discovered in these early sensory and telegraphic systems. Our most complex, high-level theories of information are deeply, undeniably rooted in the literal meat space of the human body. Which leaves us with a truly fascinating question to ponder. If the foundational math of computing was born from the struggle to push discrete symbols through the narrow bandwidth of a human fingertip or an acoustic ear, is our entire digital reality today just an incredibly advanced physical workaround for our own biological limits? Think about that the next time you tap a screen. Thank you so much for joining me for this explainer. Keep learning, and as always, look past the screen.